Session on advanced public key encryption. So we have 4 talks in this session. Our first talk will be on tight adaptive simulation security for identity-based interproduct functional encryption in a quantum random oracle model by Tema Edamura and Atsushi Takayasu. And Atsushi will be giving the talk.
Thanks for the introduction. I'm Atsushi Takayasu from the University of Tokyo. And the title of this talk is the tight adaptive simulation security for identity-based interproduct FE in the quantum random oracle model. And this is a joint work with Tema Edamura. Okay, in the inner product functional encryption, IPFE schemes, the key generation authority runs the setup algorithm, which takes the L denotes the dimension parameter as input, and publish the master public key. And the encryptor uses this master public key and encrypts the message X. X is the L-dimensional vector. Then the user secret key depends on some L-dimensional vector Y, and the decryption result of the ciphertext of X by the secret key of Y becomes the inner product between X and Y. And there are 2 flavors of security definitions. There are int-based security and the string-based security for IPFE. In the int-based security, PPT adversary A with some secret keys SKY1 to SKYL-1 cannot distinguish 2 ciphertexts of X star 0 and X star 1, such that the inner products of all X star 0, X star 1, and all secret keys are the same. If they are the same, the int-based security ensures that these 2 ciphertexts are indistinguishable. In contrast, in the string-based security, adversary with the same secret key and the challenge ciphertext cannot learn anything besides the inner product values between this X star and this Y. This is a string-based security, and the string-based definition is natural and stronger than the int-based one. So when we consider the IPFE research, we want to construct adaptive simulation-based secure IPFE schemes. Okay, so we want to review the previous works of IPFE. Although there are several works, the state of the work is presented by LMT PKC 2.0. In this work, the LMT paper proves that the previous ALS-16 DDH-based schemes and the DCR-based schemes satisfy the adaptive simulation-based security. Adaptive simulation-based security. And in addition, this paper also proposes a generic transformation from 2L-dimensional insecure IPFE schemes computing inner product modular prime P to be an L-dimensional simulation-based secure scheme. So, since the ALS-16 proposes other insecure LW-based schemes computing the inner product modular prime P, by applying this transformation, we can obtain the other sim-secure LW-based IPFE schemes. Okay, next, there is an identity variant of the IPFE, which we call the IB-IPFE. The encryption algorithms and the key generation algorithms of IB-IPFE takes the identity as the input, and the decryption works correctly if these identities are the same. In that case, we can recover the inner product between X and Y. And there are 2 main works of the IPFE, AZCU 2.0, and sorry, it should be the LLW, I guess, LW21. And also several SXDH-based schemes and LW-based schemes have been proposed, but all the schemes are either the adaptive int-based security or the selective simulation-based security. I mean, there are currently no adaptive simulation-based secure IB-IPFE schemes. In addition, all these other insecure schemes or the selective simulation-based secure schemes do not have tight reductions. They suffer from some reduction loss. Okay, so in this paper, in our work, we propose the first adaptive simulation-based secure IB-IPFE schemes with tight reductions from the DBDH assumption and the LW assumptions in the quantum random oracle model. As a first result, we propose adaptive simulation-based secure DBDH-based schemes. This construction is to be honest, not very technical. We just combine the columns, DBDH-based tightly adaptively secure IB schemes in the RAM, and LS16 DDH-based AdSim secure IPFE schemes, and we can obtain the tightly adaptive simulation-based secure DBDH-based IB IPFE schemes. The next result is not the AdSim secure, but the add-in secure LW-based schemes. First, we review the previous ACGU20 schemes in detail. These IB IPF schemes in the random oracle model computes the inner product over the integers. And this construction is a combination of GPV IBE secure in the RAM and the ALS IPFE computing inner product over the integers. In contrast, we propose very similar but different IB IPF schemes which computes the inner product modulo prime P. Our IB IPF scheme is a combination of KYY, Katsumata Yamada Yamakawa's tightly adaptive secure IB schemes in the RAM and ALS16 IPFE schemes which compute our inner product modulo prime P. And since this KYY IB is a slight modification of GPV IBE, although there are ACGU schemes and our proposed scheme is very similar, but our scheme achieves a tight add-in security and computes the inner product modulo prime P. Okay, so the next contribution, to summarize, now we have a tightly add-in secure LW-based IB IPFE schemes in the QRAM modulo prime P. And based on the LMTs into SIM transformation, we can obtain SIM transformation from two-dimensional insecure IB IPFE schemes to be computing in a product modulo prime P to be an L-dimensional simulation-based secure scheme. So based on this LMT20, we can obtain the AdSim secure LW-based IB IPFE schemes. But in this work, we find a better way to achieve the simulation security. We propose a new into SIM transformation for IPFE and IB IPFE. Our transformation is a generic transformation from not 2L, but L+1 dimensional end-based secure schemes to be end-based secure schemes computing inner products modulo prime P to be an L-dimensional simulation-based secure schemes. So based on the proposed transformation, we obtain LW-based, the first LW-based tightly AdSim secure IB IPFE schemes, and we also improve the efficiency of the state-of-the-art LW-based AdSim secure IPFE scheme. And since, in my opinion, this transformation is the main result of this paper, in this talk, I want to present this into SIM transformation for IPFE, not IB IPFE, but IPFE for simplicity. Okay, first we review the definition of AdSim security for IPFE. AdSim security requests that the real security game run by the real algorithm setup keygen, enc, and keygen is indistinguishable from the ideal security game run by the simulation algorithm setup keygen, enc, and keygen. At first, the challenger runs the setup algorithms, and the adversary receives the master public key and the pre-challenge secret keys created by the real algorithm or the simulation algorithms. Next, the adversary also receives the challenge ciphertext and the post-challenge secret keys by running this algorithm or these algorithms. The essential difference is that in the real security game, the encryption algorithm takes the challenge message X star as input. But in the simulation algorithms, the simulation encryption algorithm doesn't take the X star as input. In turn, it takes the inner product value between the pre-challenge secret key, denoted by ZI. Then, in addition, in the simulation post-challenge key generation algorithms, it takes not only the vector yi, but the inner product value between the challenge message. So, I want to say that for simplicity, we assume that this vector yi, y1 to yl minus 1 is linearly independent in this talk. Of course, in our paper, we consider the general case, but in this talk, we consider the case that they are linearly independent. And so the add-sim security ensures that inner product values are only not the X star, but only the inner product values are sufficient for simulating the real security game without the challenge message X star. It means that the real security game does not leak anything besides inner product value Zi. Okay, so next in this talk, we only consider the case that the setup algorithm and the pre-challenge key generation algorithms are the same between the real security game and ideal security game. And in this case, we run the same setup algorithm, same pre-challenge key generation algorithms, and the enc and post-challenge key gen are not the same. And to prove the add-sim security, the decryption consistency is required for the simulation algorithm. It means that although the simulation encryption algorithm does not take X star as input, but only the inner product value, the decryption results should be consistent for this inner product value, correct inner product value. In the same way, since this is a public key IPFE, the adversary can create any ciphertext for any message X. So all secret key should compute the correct inner product values. Okay, next we review the LMT transformation, which transforms the 2L-dimensional in the secure scheme to be our L-dimensional simulation secure scheme. The simulation secure ciphertext for the L-dimensional vector X is in the secure ciphertext for this vector X in the first L coordinates and 0 in the last L coordinates. And to create a secret key, we use random values Ti to TL minus I. They distribute uniformly over ZP. And to create the first secret key, sim-secure secret key for Y1, L-dimensional Y1, it becomes the N-secure secret key for this vector, the Y1 in the first L coordinates and 1 in the next, and 0, 0, 0, and in the last coordinates, we have the random value T1. So in the ith simulation secure secret key for the L-dimensional vector Yi, the first L coordinates is Yi, and the others are all 0, except the ith position is 1, and the last position is Ti. This is the real algorithm of the LMT transformation. And the simulation algorithm of the LMT transformation only changes which vector to use for the simulation-based secure schemes. So we only consider which vectors to be used. We use this vector for the pre-challenge secret key, and this vector for the real encryption algorithm, and this vector as the post-challenge real key generation algorithms. And in the simulation encryption algorithms, since it does not use the X star, in turn, it first computes the X hat such that the X hat and this Yi becomes the correct inner product values for all pre-challenge secret keys. Then sets this vector as the challenge ciphertext. X hat in the first L coordinates and minus random elements and 1. Then the post-challenge secret key queries, they are the same as the real secret key vector, but the last coordinate Ti is replaced with the Ti plus Zi minus the inner product with this X hat. Not X star, but the X hat. And this construction satisfies the decryption consistency. When we consider the inner product between this vector and the real vector, then the inner product becomes inner product between x hat, yi, and minus ti and ti vanishes, and we have the correct inner product value zi. Next, when we consider the inner product between this challenge ciphertext vector and the post-challenge secret key vector, we have the minus ti plus ti vanishes, and this inner product between x hat and yi here and here vanishes, and it becomes the correct inner product value zi. This is empty transformation. And to prove the security, the proof consists of two steps. In the first step, when we replace the real key post-challenge key generation algorithm with the simulation key generation algorithms, it's changed that the ti becomes this value. But the randomness of this ti ensures that this last coordinates follows uniform. So these two games are statistically indistinguishable. Then finally, the decryption consistency ensures that even when we replace the real encryption algorithms with the simulation encryption algorithms, the insecurity of the underlying IPFE schemes ensures the change. Okay, so for the element transformation, to ensure the decryption consistency, this vector is used for the challenge ciphertext. And the first L coordinates x hat depends on zi, since it satisfies this equation. And the next L minus 1 coordinates depend on the random ti's. And so that we can replace the post-challenge key generation with the simulation algorithms, the random ti is used to ensure the last coordinates. This last coordinates follows uniform for the simulation post-challenge key generation algorithms. Okay, so in turn, to construct the simulation secure scheme from only not 2L but only L plus 1 dimensional insecure schemes, we utilize the first L coordinates depending on both zi and ti. Here it depends only zi and it does not depend ti, but in our construction, the first L position depends on both zi and ti. And then we will set the last coordinate of the post-challenge secret key query as zi minus this inner product value. It means that in our transformation, there is no random ti to randomize the last coordinate. So in turn, we embed the random elements in this x hat, the first L coordinates of the challenge ciphertext. Okay, so let's go to our real algorithms. Our real algorithms, it takes the L plus 1 dimension. It is yi and ti in the pre-challenge key generation algorithms, and x star 0 to create the ciphertext. This is also the yi ti. And in the simulation encryption algorithms, we first compute x bar. Inner product between x bar and yi becomes zi minus ti modulo p. And we also compute some x halves. And these vectors are also orthogonal to the yi for the pre-challenge secret key queries. Then we set this vector as to create the challenge ciphertext. The first L coordinates x hat equals x bar plus this s times x halves. And the post-challenge secret key can be created by using this vector, yi and zi minus the inner product. Okay, so to show the proof, this is a pre-challenge secret key query. This is the challenge ciphertext. Then this is a vector for the post-challenge secret key queries. And what we have to care is that the decryption consistency holds. Although we have this random SJ here, but when we consider the inner product between this vector and this pre-challenge secret key vector, since this x harp is orthogonal to all yi, this inner product becomes the inner product between x bar yi plus ti. So it becomes the correct inner product value zi. And by this construction, the inner product between this challenge ciphertext vector and the post-challenge secret key vector becomes the correct inner product value zi. And finally, although we don't have the random ti in the last coordinate, But since we have the random SJ here, the randomness of this SJ ensures that the last coordinate of the post-challenge secret keys follow uniform distribution. So this completes the brief overview. Okay, that's over. Thanks for listening.
Great. We have time for maybe one quick question. So in your construction, from indistinguishability to simulation-based security, you needed to increase the dimension of the vector by 1. Is this necessary?
Only 1.
Or can you hope to get something even tighter, like a dimension?
I don't know. I don't know if this is optimal one, but yeah, we only use the L plus 1 dimension. We don't know the L dimensional is okay. Well, we don't know.
I see.
Okay.
Cool. Thanks. All right. So let's thank the speaker again. All right, so our second talk will be on predicate encryption from lattices, enhanced compactness, and refined functionality by Yejing Wang, Bokan Wang, Qiqi Lai, Huasheng Wang, and Yejing will be giving the talk.
Okay, thanks for the introduction. And today I'm going to talk about our recent work, predicate encryption from lattices with enhanced compactness and refined functionality. I'm Yejing Wang, and it's a joint work with Bokan Wang, Qiqi Lai, and Huasheng Wang. Okay, so a predicate encryption, or PE for short, has a really similar syntax and correctness definition with attribute-based encryption. The authority first runs the setup algorithm to generate master public key and master secret key. Using its master secret key, the authority also generates functional secret keys for the authorized users. While given the master public key, anyone can generate ciphertext for their chosen attribute X and message M. While using its secret key for a predict function F, the decryptor can try to decrypt the received ciphertext. And correctness means that when the attribute X inside the ciphertext satisfies the predict function F inside the secret key, the decryption would reveal the message M. And for a specific ciphertext with the attribute X encoded in, we call a secret key as 1K if it can successfully decrypt the challenge ciphertext. Otherwise, we call it as 0K. So for the security definition, here we take the adaptive security in the simulation-based model as an example. The challenger first ran the setup algorithm to generate master public key, and given the master public key, the adversary can try to ask for several secret keys, and at any stage of the security game, it would output its challenge attribute and message pair and get the challenge ciphertext in back. And finally, it outputs its guessing result. And for a predict encryption scheme, we require that message M is hidden if the adversary cannot decrypt the challenge ciphertext. And also, for the weak attribute heading property, we also require that message is hidden for all the non-decryptor case, which means in this case, the adversary cannot ask for any one case. Well, for a stronger notion, fully attribute hiding, we do allow the adversary to learn one case. And of course, it's a stronger notion. And for the related works, we only list the highly related works here. Agarwal in 2017 proposed a scheme achieved the security against any fixed Q1K queries in any polynomial number of 0K queries. However, in this scheme, the adversary cannot ask for any 1K after the challenge phase. And its ciphertext size grows additionally with Q squared. Also, as mentioned by Agarwal et al. In 2013, the ciphertext size at least grows linearly with the collision bound Q. So as we can see here, in Eurocorpit 2021, Lailu and Wang proposed a scheme achieved this optimal ciphertext dependence. Also, the restriction on the secret queries are removed. In this scheme, we also achieve such additional linear blowup, and moreover, both the fixed overhead and per unit expansion are compressed. Okay, so if we consider more fine-grained access control over encrypted data, we can take one step further from predict encryption to predict inner product functional encryption, or PIPFE for short. Actually, we also have a similar syntax framework and correctness requirement with PE scheme. The main difference is here, like a successful decryption would reveal an inner product value instead of the whole message itself. So correspondingly, the encryption algorithm would take input of both an attribute X and a message vector U. And also, each secret key is related to both a predict function F and a key vector V. And correctness requires that a successful decryption would reveal the inner product of the message vector U and the key vector V. Also, as in PE scheme, we for a specific ciphertext, we separate all secret keys into one case or zero case, depending on whether f of x is true or false. Actually, the security game setting is quite similar, but the message heading and attribute, mainly message heading property, is slightly different because we are now considering not all or nothing encryption, right? So we require the message M to be hidden for both 0K and 1K. But if we only consider weak attribute hiding property, we still restrict the adversary to ask for any 1K. So there's still a stronger notion fully attribute hiding here, and that is what we consider in this game. Duran et al. In 2023 proposed unbounded zero and non-zero predict IPFE scheme from SXDH and bilateral scaling assumptions, while only their secret K unbounded non-zero PIPFE scheme achieves simulation-based security. And in our scheme, we not only achieve fully attribute heading property in the simulation-based model from LW assumptions, it also supports a general, more polysize fully circuit predict class. And our PIPFE scheme also inherits the optimized compactness for our underlying PE scheme. Let's quick recap the technical background. These two schemes actually they finally achieve the same security level, and it's both starting from the partially hiding PE scheme with only weak attribute hiding property. Algora first construct a very selective secure PIPFE scheme, allowing a single 1K query. And then this very selective scheme is then upgraded to achieve semi-adaptive security by using IPFE scheme. And then after that, the carry-freeness helped the scheme to further support Q1K queries. Well, on the other side, Light et al. First introduced a novel technique called two-stage sampling, which enables their underlying PHP scheme to directly allow one more 1K queries. And then after that, using a novel cover-free set sampler and existing upgrade technique, they can also achieve Q-poly semi-adaptive secure PIPFE. While in this very end step from PHP to PE scheme, they actually choose the same technique. To explain this, maybe we should quick recap the attribute encodings and homomorphic evaluations. So we have these two algorithms, evolf and evolfx. Evolf would take inputs of attribute encoding matrix and outputs a matrix H sub f. And evolfx algorithm would additionally take input of an attribute x and outputs a matrix H sub fx. And if we first compute this attribute encoding matrix minus xo times g, and right times this matrix H sub fx on the right side, the whole result would be equal to this attribute encoding matrix times H of f minus f of x times g. So we can use this homomorphic property to construct attribute-based encryption. And in most case of attribute-based encryption from lattices, the attribute X would be encoded in this form. So the orange box is the same as the last page, and we just compute some secret vector ice, and we compute ice transpose with this orange box term and add some noise term. Here we use the underwave to denote the noise terms. And rely on the homomorphic evaluation properties, we would get the result. And when f of x is 0, the result would contain no information about x, which makes us maybe generate secret keys during the key generation, because we do not know any information about x at that time. And if we want to further hide the achieve attribute hiding property, we can use GSW13 FHE scheme to first encrypt attribute X, and then we generate encodings for this encrypted result. Also, we can rely on the homomorphic evaluation properties, but it turns out that we can only get the encrypted result of this f of x, but we want it in plain form. So we need to first evaluate and then try to decrypt it. So what we can do is maybe we additionally contain the secret key of homomorphic encryption scheme as another part of attribute, and we generate the attribute in the encoding for this whole attribute, and then maybe we need to slightly adjust the homomorphic evaluation process, but at the very end we can get this plain result of f of x. Everything seems goes fine, but actually the partially hiding P scheme only support a very special predict class, which means if we take input of both as x public and x private, it first computes C of x public and then outputs inner product of x private with this C of x public. So, but actually the FHE decryption is not just a simple inner product function, it's threshold inner product. So we need to set the predict encryption secret key as a bunch of secret key in the underlying PHP scheme. And each of them is related to one possible FHE decryption noise. Of course, it will lead information, so we need to add some smudging noise to prevent from leakage, and that will be some dummy FHE ciphertext as another part of public attribute. Well, actually, we have another technique, which is a very interesting method proposed by Barkowski et al. This technique is called a dual use. To see this, also we need to hide this attribute first by using FHE scheme. But when we generate the encoding for this encrypted result, we do use that as a secret as, both as the secret of encoding and the FHE secret key. So we will rely on a slightly different form of eval-f and eval-fx in the matrix form. And also we have such homomorphic evaluation property. And if we rewrite this result, it turns out that we get actually what the FHE decryption look like. So this encrypted result would be automatic decrypted without needing further operations. So that's why we choose to start from this weak attribute hiding PE instead of partially hiding PE. And we also notice that two-stage sampling technique is also applicable in our case. And by using cover freeness and generic upgrading technique, we can also finally get this result. And because we avoid of using both lazy-R technique and adding smudging noises, our resulting secret key is independent of FHE decryption noise. And we also reduce this fixed overhead and per unit expansion. I will briefly introduce how we construct the IPFE scheme. Actually, we first attempt to follow in the similar approach as we done in constructing PE, which means we first allow the scheme to support a single one-key query with selected security, and then following this approach till the end. And to get a starting point, maybe we can, a natural idea would be how about combine the PE scheme with IPFE scheme? Like PE will supply an outer framework to supply attribute-based access control and attribute heading property. And inside of this, IPFE would support inner product functionality. However, it turns out that it cannot work. The main reason is we do rely on dual use technique in our underlying scheme. I will not get into details this time, but situation is we need this FHE public key to compute X first, and then using the result ciphertext to program attribute encoding matrix during the setup phase. However, if we want to reduce the security to IPFE scheme, the complete FHE encryption key is only known until the challenge phase. So yeah, to fix this, we rely on useful fact that for GSW13 ciphertext, its upper part, except for its last row, actually does not include FHE secret key. So we can encrypt the attribute X once more with different FHE secret key, but the same FHE randomness. And yeah, we will get this result. But if we want to achieve simulation-based security, cover freeness, this property itself is not sufficient because we require additional programming space to insert information either in the ciphertext or in the secret case. So also by this paper, I think the first talk already discussed about it. And anyway, inspired by this technique and also combine our usage of cover phrase site sampler, we noticed that 2 more dimensions is sufficient for our construction goal. So at the very end, we can still rely on this generic upgrading technique to guide this final result. And that's all for today. Thank you.
Great. We have time for questions. So, are there any? So I have one. So when you talk about the predicate encryption, the scheme only supports bounded depth circuits, right?
Sorry,
Yeah, do you assume there's a priori bound on the depth of the Boolean circuits for your construction?
Yeah. It's also I'm not sure if I should contain this as an open problem or future direction because I noticed that the technique for achieve unbounded depth AB scheme, they can get unbounded PE scheme, but that technique can only allow us to get a weak attribute heading PE.
I see.
So I'm not sure if it's interesting to think whether we can get an unbounded depth circuit PE scheme with a strong attribute heading property.
I see. Okay, great.
Okay,
It's an interesting open question. Cool.
Okay,
Any
thanks.
other questions? All right, if not, let's thank the speaker again.
Okay, thanks.
Well, do you want questions at the end, or would you prefer to just defer to the authors?
No, it's all right. I can try to answer, and if it's too technical,
Okay.
I simply
All right.
refer to
Sounds
the
good.
authors.
Okay. Thanks. All right. So our third talk will be multi-client functional encryption with public inputs and strong security by Kai Nguyen, Duan-Hugh Fan, and David Ponkawal. And the talk will be a proxy given by Robert Shadrick.
How do I get the laser pointer?
It's not a presentation.
Sorry, this might have been me. Okay, hi everyone. This is a joint work by Nguyen, Yufan, and David Ponkawal, and I'm the proxy speaker replacing Key, who thankfully prepared the slides for me. And And so I will start with a brief introduction of the primitive multi-client FE. Then I will explain two features of previous works that have been achieved independently. And then I will explain the contributions of this work, which is essentially a combination of these two techniques that have been achieved before. And in the end, if time permits, I will highlight some technical details. Okay, so very generally speaking, I think it is fair to say that our technical ecosystem is quite complex, ranging from critical infrastructure to Internet of Things, and everything is somehow connected through web and cloud services. And so we have a variety of a lot of different requirements regarding data protection, many different functionalities that we want to achieve, and we need scalability to deal with a large amount of data. And from a cryptographic perspective, we want many different things as well, like authentication, confidentiality, data integrity. We need systems with many users, and we want fine-grained analysis in the sense that we want to understand in detail which piece of information is leaked to which user in the system. And one primitive that allows to tackle a subset of these requirements is multi-client functional encryption. Here we have a bunch of encryptors that are called clients. I think on the slides here they are represented by these houses. And each client has their own encryption key to independently encrypt their share of the data. And then similar to the previous talks, we have essential authority that can generate decryption keys for certain functionalities, with the difference being that now this functionality has arity n, where n is the number of the clients. And so in the end, we can take a tuple of n ciphertexts, one from each client, and use the secret key for functionality f to learn f of the plaintext data. And one special thing here is that we additionally encrypt with respect to a tag, and so encryption is only permitted if all the ciphertexts that we want to jointly decrypt, they all must share the same tag. For example, the tag can be a timestamp, and in this way we can make sure that only data that, I don't know, was encrypted on the same day or the same month can be jointly decrypted, and we cannot evaluate data that doesn't belong together. Okay. And so, as one might expect, the complexity to build such a scheme heavily depends on the kind of functionality that we want to evaluate. And one functionality that has been studied a lot in the literature and that we already saw in previous talks is the inner product functionality. Here, each client encrypts a short vector, and our global input data is just the long vector that is the concatenation of all the short vectors. And our function is also described by a vector, and in the end, decryption recovers the inner product between the two. And so one question that comes to mind immediately is if we want the encryption keys of the clients to be public or secret. And I guess it would look natural to aim for a public encryption algorithm. Unfortunately, this is not possible. So, for example, in the case of the inner product functionality, the adversary could use these encryption keys if they were public to encrypt, for example, zeros for x1, x2, x3. And in this way, the decryption result would be just x4, y4, y4 being public part of the function. So x4, which is supposedly secret, is completely leaked. So unfortunately, we cannot have public encryption algorithms in this model, and we need to go for secret encryption. However, this is not very favorable either, because then, phrasing this differently, only a single secret key of one client has to be leaked to completely, and we would lose all security guarantees. And so what we do is we use something in the middle, where by default secret keys or encryption keys are secret. However, the adversary has the ability to explicitly corrupt certain keys, and the more keys are corrupted, the weaker the security guarantees that we can provide. But this is somehow the best we can do. This I will say later. Okay, and so now there are two independent features that have been considered in previous works. One is actually very similar to the previous talk, where besides the plain inner product functionality, one might ask for additional control on how decryption keys can be used. And so in this work from AsiaCrypt 2020, the authors equipped plain inner product FE with additional access control, meaning that for the ciphertext, we encrypt the vector along with an attribute, and the ciphertext, the key vector is also equipped with a policy, and we can learn the inner product if and only if the attribute of the ciphertext satisfies the policy of the key. And so this first work considered the case of single and multi-input FE, and in a follow-up, the authors of the current work extended this to the case of multi-client functional encryption, where they also provided a construction for MCFE for scalar inner products, meaning that each client could encrypt one scalar only, and policies were captured by linear secret sharing schemes. And so the second additional feature that I mentioned is about the security model. However, defining security for MCFE is a bit tricky, so let's look at the single client case first. Here we have only one encryptor, and we have an authority that generates decryption keys, and decrypting the two together gives F of the data. And for security, we allow the adversary to obtain decryption keys for certain functionalities, say F, G, and H, and then we want the usual indistinguishability-based security game where the adversary submits two challenge messages, M0 and M1, and we require encryptions of the two to be indistinguishable. And to make the security game meaningful, we need to exclude certain trivial attacks. In particular, what we need to do here is we must require that the two challenge messages M0 and M1 evaluate to the same function value under all functions, F, G, and H, where the adversary has a secret key for. If we would not do this, then the adversary could simply take the challenge ciphertext, decrypt it using one of the legally obtained decryption keys, and look at the decryption value to decide the security game. Okay, so now the multi-client case. It's similar, but yeah, we have to deal with several clients. First, we still have this key generation oracle that sometimes is called extract. Here, the vector y describes a function in a product functionality. Then we have the previously mentioned corruption oracle, where for some slot I, the adversary can query for the encryption key. And we have a challenge oracle, where for some slot I and attack, the adversary submits two messages and obtains a challenge ciphertext. And so then for technical reason, we also need an encryption oracle to upgrade from single challenge to multi-challenge security, but this is not too important here. And so in the end, the adversary submits a guess, B prime, and wins if and only if B is equal to B prime, where B is the challenge bit. Now, the interesting part again here is how do we define admissibility, meaning which trivial attacks do we need to exclude. And the first condition here is what we have already seen on the previous slide, now written down explicitly for the inner product functionality. And the other thing that changes is that in the single client case on the previous slide, we had only one input. Now we have x0 and x1 being basically the concatenation of all the x0 i's, x1 i's for all slots I. So x0 and x1 here, I think, denotes the concatenation of all the challenge queries for all slots. Okay, so this is not new. But what is we need to consider in addition for the multi-client case is that we need additional restrictions for the corrupted slots I. And yeah, previous works glossed a bit over this issue by just saying, okay, we do not allow challenge queries for corrupted slots I at all. We just want x0i and x1i to be identical. And surprisingly, a lot of follow-up works simply adapted this and did not care about corrupted slots. And so the justification that was given for this is that they say, okay, multi-client FE, as we have said, is a secret encryption algorithm. oftentimes it is deterministic, and if we go for a deterministic encryption algorithm, then yes, indeed, we need this strong condition, because otherwise the adversary could simply rerun the deterministic encryption and compare the result to the challenge ciphertext to break the security game. However, this looks a bit unnatural because nobody forces us to use deterministic encryption. We could just go with probabilistic encryption. And therefore, the question is if we can't do better. And so doing better means we would like to weaken this condition, which would allow for stronger attackers that can ask more oracle queries, which would result in a stronger security model. And so this has been considered before in a work, again, by the same authors as this paper from ACNS 2023, where they said, okay, so the first condition again does not change because this is what was considered in all the previous works as well. However, they are able to weaken this condition on corrupted slots. And in addition, they provide a optimality proof in the sense that they show that any additional query that was permitted to the oracles would result in a trivial attack against the scheme. And so now what is done in this paper is basically a combination of these two features. They provide a scheme for the inner product functionality with access control. And in addition, they want to achieve this optimal admissibility notion. And the first thing that they notice is that there is a slight syntactical problem, because security, as I have just defined it, means so only considers like secret inputs where we attempt to hide the entire data, but if we want something like ABE, then this doesn't really fit, because usually the attribute can be public. And so to capture this, they first refine the syntax of MCFE by explicitly allowing public inputs, and then they combine it with this optimal admissibility notion. And in particular, what they observe is that MCFE with optimal security implies public key functional encryption, even if MCFE itself has secret encryption. And once we have public KFE with public inputs, then of course we also get ABE with public attributes and so on. And so my personal interpretation of this, maybe the authors disagree, but my takeaway here is that these implications for me look somehow natural, because I mean, obviously MCFE is a more complex primitive than single client FE, and FE again is more complex than ABE, so yeah, certainly we should have implications like this. However, I think what the authors want to point out is that if we are not careful which syntax and security model we actually use, then it might happen that these implications that we think we have are maybe not that easy to write down formally. And in terms of contributions for constructions, they have a new MCFE scheme for inner products from pairings in the random oracle model, and they have a stronger security model than all the previous works, combining access control with this optimal admissibility notion. Okay, so now next I want to explain these implications in a bit more detail. And so I think, so let's first have a look at the concrete optimal admissibility that they have in the case of inner products. So here the solid boxes denote the secret inputs of honest I. This is the input of a corrupted I, and these dashed boxes are the function vectors. And so for honest I, we basically require the same thing as before, where we want the function values to be equal for all y vectors that were queried to the key generation oracle. And so this sum is basically the global function evaluated on all I in the case of inner products. And the second condition is the condition for corrupted I. And here we can see a difference to the previous works. If you remember, I said that most of the previous works considered a very strong condition here, saying that x0i and x1i must be completely the same. which gives basically no security for corrupted slots. And here they can relax this and only require that the, I would say, the local evaluation of the function, which in this case is the inner product and slot I, only this must be equal. But x0i and x1i can be different. And why this is interesting can be seen when we look at these implications of this work. So to recall, the authors of this work build an MCFE scheme with public inputs and strong admissibility. And so first we can consider the special case where the number of clients is 1, so very special case. And then we can consider the case where this single slot is corrupted, which means that the encryption key of the single slot is given to the adversary, which basically gives a public key scheme. And then we can look at the strong admissibility from the last slide, which gives a condition that matches exactly the admissibility of the public key functional encryption. So this is how we get public key FE from secret key MCFE with strong admissibility, and compared to the previous works, they would only require x0 being equal to x1, which basically disallows all challenge queries, and we wouldn't obtain any security in this case. Yeah, and then we have other implications that I mentioned before. Once we have public key FE with public inputs, of course, we can use this to obtain ABE as well. And going back to MCFE, we can also fix one tag and obtain MIFE. What is important here is that we allow so-called repetitions, which means that for a certain I and some tag, we can ask more than one queries, because there are a lot of works in the literature that consider MCFE in a weaker variant where we are allowed to ask only one query per tuple of I and tag. In this case, we would not get MIFE, but here we do. With one restriction, this work still has the limitation that for each tuple of slot and tag, we can ask only one public input to the oracle. And therefore, the implication to MIFE is only the vanilla version, where we have plain inner products, still with the optimal admissibility, but we cannot realize attribute-based access control currently. So now I'm running out of time, so let me skip the last slide. Okay, and so to conclude, in this work, the authors provide a new framework for MCFE that explicitly includes public inputs, and they show that if we use the right security notion for MCFE, then we also get implications from secret key MCFE to public key FE and ABE. And in terms of construction, they extend their previous works from the scalar variant of the inner product functionality to subvectors, and in terms of security, they are able to improve on a crypto paper from 2023 by Agrawal, Tomita, and Yadav. They consider a stronger functionality called attribute-weighted sums, but they have a weaker security notion. And for future work, I think there are some natural questions. Of course, we could consider stronger functionalities like unbounded inner products, where we do not fix the length of the vectors up front. We could consider more general models like dynamic or decentralized FE, and of course it is also desirable to have instantiations from other assumptions. Thank you.
We have time for maybe one quick question. Anyone? So I have one. So do you have a sense for whether these techniques could be extended to quadratic functions or higher degree functions?
So for quadratic functions, I think the best we currently know is MIFE. Mm-hmm. We don't have MCFE, so we have either, we can either support labels or corruptions, but not both at the same time. There was a TCC work by Shweta from Agrawal from, I don't know, 2-3 years ago. And if I feel like, so my personal feeling is that getting this quadratic MCFE with the techniques that they use probably would also give us an attribute-based MCFE for inner products, that is also open. So I feel like combining tags with repetitions on the public inputs is an open problem, which I feel like is also connected to the quadratic case.
Cool, great, thank you. So let's thank the speaker again. All right, so our final talk in this session will be on key revocation and registered attribute-based encryption by Kyoichi Osano, Nutapan Atrapadan, Kisuke Hara, Kitaro Hashimoto, Yohei Watanabe, and Kyoichi will be giving the talk.
Thank you for the introduction. I am Kyoichi Asano from the University of Electrical Communications. In this talk, I present key revocation in registered attribute-based encryption. This is a joint work with Nutapan Atrapadan, Keisuke Hara, Kitaro Hashimoto, and Yohei Watanabe. The main topic of this presentation is variants of attribute-based encryption, so I explain about it first. So attribute-based encryption, ABE in short, is a kind of public key encryption which enables fine-grained access control on encrypted data. In ABE, there is a private key generator which has privilege to generate a user's secret key. When encrypting a message, a sender specifies the ciphertext attribute and runs the encryption algorithm. Then the receiver can decrypt this ciphertext with a corresponding secret key such that the predicate holds. While ABE is such a useful primitive, but it has some major issues known as key escrow issues. The key escrow issues arise from the fact that PKG holds a master secret key. Since the master secret key can generate secret keys for all attributes, then the PKG can decrypt all ciphertext. Even if the PKG is fully trusted, it could still become a single point of failure because of some attackers in outside. As one of the countermeasures against the key escrow issues, Hohenberger et al.'s proposed registered attribute-based encryption, RABE in short. In RABE, there is no third party which has a privilege like the PKG in ABE. Instead, there is a transparent key creator in KC in short, whose operations are deterministic and does not hold any secret information like the master secret key. After the registration, the KC, so therefore, while in ABE, the PKG generates a user secret key, but in RABE, user generates a secret key and registers the public keys to the key creator. And after the registration, the key creator aggregates the public keys into the compact master public key. This key, here the master public key is updated each time registration occurs. So the receiver needs auxiliary information called a hypersecret key to decrypt the ciphertext correctly. And this hypersecret key can be obtained from the key creator, and frequent update is impractical, so the few updates is desirable. RB resolves the key escrow issues by removing the PKG from ABE, but there are still some issues remaining. In RABE, once the user is registered, they remain part of MPK permanently. So when considering long-term use, there is a risk that the user's secret key may be compromised. Specifically, in attribute-based setting, key compromise can affect the security of other users, since multiple users may have the same attributes. So in this work, we consider that key revocation is necessary. However, no existing library scheme considers the key revocation. Closely related work is deletable registration-based encryption, which was proposed by Fioretto. But they only define model and security notions without showing any concrete construction. So in this work, we provide fast formalizations for two distinct notions, RV with revocation. First is a deletable RV, in which cache deletes a registered public key from the master public key. And second is a directly revocable RAV, in which a sender can directly specify a set of revoked users when encrypting a message. And we propose a generic construction of deletable RAV from slotted RAVE. Our construction is based on the complete substring method and Hohenberger et al.'s generic construction of RAV from SRV. Since Hohenberger et al.'s construction is the main approach to obtain the RAV schemes, so there are many slotted RAV schemes. So we can instantiate various deletable RAV schemes, which includes pairing-based ones and those that support an unbounded number of users. And we also propose a semi-generic construction of directly revocable RAV for Boolean formula. In this presentation, I will only talk about the deletable RAV due to the time constraints. So what is a deletable RAVE? Deletable RAV is a RAVE which allows to delete registered users from the master public key. When deletion request is received, the key creator deletes keys from the master public key and updates the master public keys. And as in RAV, this aggregate key must be compact, but now it depends on the number of deleted users. Regarding the update efficiency, the constraint restriction is the same as in RAV. It means that the number of deleted users does not affect the update efficiency. The advantage of this deletion method is that sender can encrypt a message without knowing the deleted users. And of course, this deleted user cannot decrypt this ciphertext even if the secret key satisfies the predicate. Let us look into the overview of our construction. Our construction is based on the Hohenberger et al.'s construction of RAV, and briefly speaking, it applies a power of 2 method to slotted RAV. In this work, we extend their technique to work on a complete binary tree. And then we apply the complete subtree method. Then finally, we can obtain the deletable RAV. So before going into detail about the deletable RAV, I explain slotted RAV and the Hohenberger et al.'s construction. This is a slotted RAV. We can see a slotted RAV as a static version of RAVE, which means key creator can aggregate public keys if and only if all users are registered. In SRVE, there are slots, and each user corresponds to the slot. So user 1 corresponds to this slot, and user 2 corresponds to this slot, and so on. And as in RAV, the aggregate key also must be compact. The next is Hohenberger et al.'s construction. as I mentioned earlier, almost all existing RV schemes are constructed using this approach. The construction applies a power-to method to L+1 SRV instances, each having these slots. I explained the procedures of registration in a concrete example. Initially, the MPK set to be empty, and then add user 1, and this slot becomes full, so the KC aggregates and obtain the MPK 0, and this is the current MPK. Then add user 2, and this highlighted slots become full, then the KC aggregates and obtain the MPK 1, and use it as a MPK, and remove the MPK 0, and yes. I want to note that this MPK 1 covers user 1 and user 2. Then add user 3. Now this slot becomes full, then the cache aggregates and obtain the MPK 0 and append it to the MPK. Finally, add user 4, and these highlighted slots become full, so the cache use this MPK 2 as a MPK and clears the other slots, and this MPK 2 covers user 1 to user 4. Here, MPK consists of at most L+1 SRVs master public keys, so the compactness of RVs follows from that of SRVE. So how can we implement a deletion feature in Hohenberger et al.'s construction? Naive idea is that reusing the previously generated selected RV's master fabric key. Since no master fabric key is generated in this approach, the update efficiency is unaffected. And these slots are previously generated in the by the cache. And when I want to delete a user 4, we can use this highlighted slot. But when I want to delete user 1, there is no SRV's master fabric keys, only cover user 2 to user 4. So the cache needs to generate new SRV's master fabric keys. It affects the update efficiency. So in our research, we use a complete binary tree to handle a deletion of any user. The main difference in the procedures of registration is that users' fabric keys must be registered in each instances, while not in the Hohenberger et al.'s construction. So I also explained the procedures in a concrete example. At user 1, this is the same, and at user 2, these slots and these slots becomes full, so aggregate these fabric keys and obtain 2 master fabric keys. But the key creator only use this MPK2 as a MPK. And at user 3, this is the same, and at user 4, now these slots and these slots and these slots becomes full, so the cache aggregate these 3 and obtain the 3 master fabric keys. But cache only choose MPK 1. Then when I want to delete a user 1, the cache chooses this highlighted slot, which does not include user 1's fabric key. This is exactly what the complete subtree method does. So we can say that MPK consists of order m log n over m SRV's master fabric keys based on the discussion of the complete subtree method. So as I mentioned earlier, since the Hohenberger et al.'s construction is many approach, and there are many SRV selected RV schemes, so we can obtain the various deletable RV schemes. For example, the schemes supports various predicate, and which is post-quantum secure, and which supports unbounded number of users thanks to strong assumptions. And let me conclude this talk. We propose a deletable RAVE and directly revocable RAVE. And we also propose a generic construction of deletable RAVE from structured RAVE. Since our construction inherits the predicate underlying SRV support, so we can obtain the various DRV schemes. And I have not explained in this talk, but we also propose a semi-generic construction of directly revocable RAV for Boolean formula. Please check our paper for more detail. That's all. Thank you.
We have time for a couple questions. Anyone?
Can you somehow avoid that the master public key grows with the number of deleted users?
Yes. Yes.
So yeah, get rid of this factor of m here.
Sorry.
So your master public key, as I understood it, grows with m.
Yes.
The number of deleted users. Can you somehow? So is this necessary, or is there some way to get this a construction where this doesn't happen?
We consider that it is necessary with restriction that update efficiency does not depend on the deleted users. We observe that revocable attribute encryption, identity encryption, and broadcast encryption, the almost all schemes depend on the deleted number of users. So
Okay.
almost the same.
And if you sacrifice the update efficiency, like if you're fine with more updates or that updates are needed when users are deleted, can you then get rid of it?
Maybe, but I think that it is difficult to consider the balancing.
Okay, thanks.
Any other questions? So I have one question about the server state. So in your construction, this amount of state that the server now has to maintain, or the key curator has to maintain, is quadratic in the number of users, right? Versus in the original registered ABE schemes, I think it was linear or quasi-linear. So do you think that there's a hope of reducing the amount of state that the key curator has to maintain while supporting revocation?
So your question about the size of the...
Right, so how much information does the server have to store?
So almost the same, but we additionally add these nodes. So but constant, but not constant, but 2 times maybe.
Is it a factor of 2? Because in the previous approach that you described, each scheme only supports 2 to the I users, right? Where I goes from 1 to, let's say, log L. So that would, the total number of schemes would, or the total number of keys that you would have to store would be roughly 2 times L. But here you would have a scheme, each scheme would have to store the full number of users, so L users, and you have L of these schemes. So
Yes. Yes, we need to store all keys, so so I cannot calculate immediately. So
I see. Okay, maybe we can take it offline then. All right, so let's thank the speaker again and all the speakers in this session.